It is 9:00 a.m. on launch day.
Oh boy, the classic nightmare scenario.
Right. Your generative AI proof of concept was, it was absolutely flawless on your laptop.
Always is.
The business leaders loved the demo. The CEO has been talking about it all week. But now you've cut over the DNS. 10,000 concurrent users have just logged in.
And the underlying infrastructure just panics.
Exactly. Your Amazon SageMaker instances are caught in this brutal cold start death loop, and your sub 200 millisecond latency requirement is currently sitting at like a catastrophic 14 seconds.
Which is an eternity in AI.
An absolute eternity. The load balancers are screaming, the Slack channel is lighting up with P1 alerts, and your entire architecture is just buckling under its own weight. I'm speaking directly to the senior cloud architects listening right now. How many times have you watched a brilliant AI model get suffocated by legacy infrastructure?
We see this exact postmortem playing out week after week across the industry.
Yep.
Because the prototype phase of generative AI is deceivingly simple right now, you know? You grab an API key, you write a slick prompt, and you get a magical result.
Right. I feel like you're done.
But production reality is entirely unforgiving. When you move from a single sequential request to tens of thousands of concurrent asynchronous threads, the physics of cloud compute completely change.
It's a totally different ballgame.
It really is. The cognitive load on an architect has fundamentally shifted. For the last decade, we spent all our time tuning hyperparameters, managing underlying compute clusters, and worrying about gradient descent.
Tweaking the math, essentially.
Exactly. But today, the foundation models are largely commoditized. The engineering challenge isn't the brain anymore, it's the nervous system supporting it.
Which brings us to today's topic. Welcome to this deep dive. Today we are taking a massive stack of architectural blueprints, certification-level engineering scenarios, and battle-tested design patterns to extract the absolute optimal paths for scaling Gen AI on AWS.
And just to be clear, we aren't talking about prompt engineering today.
No, not at all. We are looking at the foundational plumbing. We're going to contrast native Amazon Bedrock abstractions with some incredibly common yet completely fatal legacy machine learning anti-patterns.
Because we really need to pull apart the systems engineering rationale behind these patterns. Before we can even worry about the cognitive accuracy of an AI, we have to guarantee that the system actually answers the network request.
Right, it has to pick up the phone.
Exactly. When a massive spike in user traffic hits at the exact same second, it has to be there. So we're going to systematically walk through the entire lifecycle of a request, from the initial compute capacity and global routing, down to the client-side streaming experience, into the retrieval mechanisms, and finally the rigid governance orchestrating the whole thing.
Okay, let's unpack this, because building Gen AI in production isn't about training models anymore. It's about orchestrating them without letting your architecture buckle.
That's the perfect way to frame it.
So let's start right at the edge of that disaster scenario I just painted. Let's talk about capacity and routing. The sources we're looking at highlight a very specific high-stakes enterprise scenario.
The customer service one.
Yeah, that one. So imagine a company developing a Gen AI application that analyzes customer service calls in real time. We are talking about generating suggested responses for human customer service agents while the customer is still speaking on the phone.
Which is incredibly intensive.
Super intensive. The baseline requirement here is processing 500,000 concurrent calls during peak morning hours. And the kicker, it needs sub 200 millisecond end-to-end latency for each suggestion.
Yeah, that sub 200 millisecond service level agreement is incredibly aggressive, but it's non-negotiable for live conversational workloads.
Why is that specific number so important?
Because 200 milliseconds is essentially the threshold of human perception.
Yeah.
If the network round trip and the token generation take longer than that, the human agent has already moved on to the next topic in the conversation.
Oh, I see.
Yeah, the AI's suggestion arrives too late, making it entirely useless, distracting, and ultimately just a sunk compute cost.
Okay, so if I'm a traditional ML architect and you tell me I need to process 500,000 concurrent requests with near zero latency, my first instinct is to grab the biggest, most aggressive compute I can provision.
Right, the brute force approach.
Exactly. I'm immediately thinking, I need an Amazon SageMaker real-time endpoint. I need a fleet of P4D instances with dedicated NVIDIA GPUs. I need raw, dedicated hardware. Why is falling back on that dedicated GPU instinct a massive anti-pattern for this specific workload?
Well, you're hitting on the core physical constraints of self-managed infrastructure. Relying on dedicated SageMaker GPU instances for this specific conversational use case shifts a monumental operational burden onto your team.
Because of the scaling.
Exactly. Let's look at the mechanics of scaling. When that morning spike of 500,000 calls hits, your auto-scaling group triggers. But spinning up a new dedicated GPU instance isn't instantaneous.
Not at all.
The underlying EC2 instance has to boot. Then, the massive neural network weights, which, by the way, can be hundreds of gigabytes, have to be loaded from disk into the GPU's VRAM. Then the inference engine itself has to warm up.
And during that whole boot sequence, which could take, what, 5 to 10 minutes?
Easily.
The incoming API requests are just queuing up at the endpoint.
Right. During those cold starts, your queue depth explodes, and your sub-200 millisecond latency requirement is completely obliterated.
It's gone.
It's totally gone. And the financial math is even more punishing. To avoid those cold starts, you would have to over-provision your baseline capacity.
Meaning you just leave them running.
Yeah, keeping thousands of incredibly expensive dedicated GPUs running 247, just waiting for a peak hour that might only last 45 minutes.
That's a CFO's nightmare.
It really is. So the AWS native approach to bypassing this entirely is Amazon Bedrock. Bedrock provides access to foundation models through a fully managed serverless API. Behind the scenes, AWS is pooling massive amounts of compute, heavily optimized for high-throughput, low-latency inference.
But wait, even with a managed service, 500,000 concurrent calls will trigger rate limiting if you just hit the public API endpoint, right? You can't just throw 500,000 requests at the on-demand pool and expect it to magically scale without throttling.
No, absolutely not. The on-demand pool is multi-tenant. You are sharing that capacity with other AWS customers. To safely handle that volume, you must transition to provisioned throughput.
Okay, provision throughput. How does that differ?
You are purchasing a reserved number of model units, or MUs, for a specific foundation model. This guarantees your capacity, isolates your workload from the noisy neighbor problem in the multi-tenant pool, and provides a predictable, consistent latency profile.
Okay, so the architect gets budget approval. They purchase the provision throughput, reserving those model units. It sounds foolproof. But our sources highlight this devastating yet incredibly common coding error here.
Oh, the model ID issue, yes.
Right. A team will spend a fortune purchasing provision throughput for an Anthropic Claude model. They deploy their code, peak hours hit, and suddenly, the Slack channels light up again. The developers look at their Amazon CloudWatch dashboards and see an absolute nightmare.
Their utilization is zero.
Yes. The provision throughput utilization metric is sitting at absolute zero, while the invoke model error metrics are throwing massive 429 too many requests, throttling exceptions. Their expensive capacity is completely idle. Why does that happen?
This failure mode comes down to a fundamental misunderstanding of how the Bedrock control plane routes traffic. Let's trace the actual API call. In the application code, the developer is using the AWS SDK, maybe Bodo 3 in Python, to call the invoke model API.
Right.
In that request payload, there is a parameter called modelAid. 9 times out of 10, the developer populates that field with the base foundation model identifier, something like anthropic.claude-v2.
Which makes logical sense. If I want to talk to Claude, I pass a string for Claude.
It makes logical sense, but it is architecturally fatal. When you pass that base model ID, you're explicitly instructing the Bedrock API gateway to route your request directly into the multi-tenant on-demand capacity pool.
Oh, wow.
Yeah. The routing engine obeys that string. It subjects you to the standard on-demand quotas, completely ignoring the fact that your AWS account actually owns reserve capacity.
So buying the capacity doesn't automatically upgrade your account's API routing?
No, it doesn't. When you purchase provision throughput using the Create Provision Model Throughput API, Bedrock provisions the hardware and then returns a brand new, highly specific provision model ARN and Amazon resource name.
Okay.
This ARN is a unique cryptographic pointer to your dedicated slice of compute. To actually use the capacity you paid for, you must go into your application configuration and replace that base model ed string with your unique provision model ARN.
I look at it like this. Using the base model ID when you've bought provision throughput is exactly like paying thousands of dollars for an elite VIP fast pass at a theme park, holding it in your pocket, but then walking right past the empty VIP entrance and willingly standing in the 3-hour general admission line.
I'm stealing that analogy. That maps perfectly to the network reality.
And then you complain to the park staff that the lines are too long.
Exactly. And the behavioral fallout from this area makes it even worse. When the development team sees those 429 throttling exceptions, their first instinct is usually to implement exponential backoff and retry logic in the application.
Right, they wrap the API call in a loop that waits a few seconds and tries again, which is standard best practice for transient network errors, isn't it? Just catch the exception and try again later.
Standard practice, yes, but in this specific scenario, adding exponential backoff to the on-demand pool while you own idle provision throughput is just putting a Band-Aid on a fractured architecture.
You're just masking the real problem.
You are artificially inflating your latency by forcing users to wait through retry loops, and you are still paying for idle GPUs. The architectural cure is tracing that single string variable, the model ARN, and swapping it.
Wow.
For a senior architect, understanding the routing implications of these identifiers is literally the difference between a seamless launch and an incredibly expensive outage.
That is wild. Okay, let's escalate the complexity. So we've solved the local capacity issue. We tracked down the string. We swapped it for the provisioned ARN. And our CloudWatch metrics look beautifully green.
Everything is humming.
The local region is humming. But what happens when our architecture spans the globe? I want to look at another scenario from our stack. Imagine an education tech company. They have a serverless AI assistant helping high school and college students summarize study notes.
Okay, classic edtech.
Naturally, students study in the evening, so the application sees massive, predictable traffic spikes that roll across the globe following the sun. 8 p.m. hits in Tokyo, the system gets hammered. Then 8 p.m. hits in London, then 8 p.m. in New York.
And if they are relying on a single region's on-demand pool, they're going to hit severe regional throttling.
Because everyone is logging on at once.
Right. Regional throttling occurs when every user in a specific geographic time zone hits the local bedrock endpoints at exactly the same time. The concurrent request volume temporarily exceeds the physical capacity allocated to that specific AWS data center for the multi-tenant pool.
But I have to stop you there. Because if I'm the lead architect and I've built global apps before, I know exactly how to solve this. I don't need Bedrock to figure it out for me. I use Amazon Route 53 with latency-based routing, or I deploy custom failover logic in my application code.
Oh, no.
Hear me out. I just read a Lambda function that says, if uCentral1 throws a 429 throttling error, catch the exception, change the endpoint URL, and immediately route the request over to us East 1 where everyone is still asleep. It gives me total programmatic control. Why are you telling me to surrender that control?
Because you are trading network control for a massive, potentially company-ending compliance risk. Custom cross-region failover logic in application code is operationally brittle. Let's look at the data residency laws governing that education company.
Oh, right, GDPR.
Exactly. If they're operating in Europe, they are subject to strict internal regulations dictating that European student data must remain physically within European borders. If your custom Lambda retry logic catches a throttling error in Frankfurt and blindly reroutes that student's sensitive study notes to a data center in Virginia just to get a faster inference response,
You have just breached compliance.
you've moved PII across international borders without authorization. Furthermore, building custom retry and failover state machines across global networks introduces immense latency overhead.
Because of the distance.
Right. Your Lambda function has to wait for the failure, process the exception, establish a brand new TLS handshake with a region across the Atlantic, and retransmit the payload.
The auditors would have a field day, and the students would still be staring at a loading screen. So what is the managed alternative?
The managed alternative is Amazon Bedrock Cross-Region Inference, or CRI. CRI natively and automatically distributes your inference requests across multiple AWS regions. It dynamically routes the workload to where there is available capacity, but it does so strictly within a defined, legally compliant geographic boundary.
So it knows the rules.
It does. You don't manage the TLS handshakes or the retry logic. The Bedrock control plane handles the geographic load balancing transparently.
But implementing CRI isn't just flipping a switch, especially in an enterprise environment. Our sources point out a very specific friction point where CRI intersects with enterprise security guardrails. Let's walk through this carefully, because the error trace provided in the blueprints is a perfect learning moment.
Yeah, the SCP collision.
Exactly. We have a developer working inside an enterprise environment managed by AWS Control Tower. The security team uses service control policies, SCPs, to aggressively lock down accounts, ensuring data stays in Europe. The SCP explicitly restricts all compute to U North 1 and U West 1.
Okay, standard security posture.
Right. Now, the developer wants to use the new Amazon Nova Pro model. They enable cross-region inference, originating the API call from uCentral-1. They hit invoke, and boom! The console throws a massive red error block. It says, action, bedrock, invoke model with response stream on resource, arn.ados.bedrock.uu-west-3. Context, a service control policy explicitly denies the action.
Let's dissect the mechanics of that error, because it really highlights how different AWS governance layers interact. The developer is sitting in Frankfurt, uCentral-1, but the error clearly states that access to Paris, US3, was blocked.
Right. Why did the request even try to go to Paris?
Because the Amazon Nova Pro model might not have sufficient capacity, or might not even be natively hosted in uCentral-1 at that exact millisecond. When the developer attempts to invoke the model using a cross-region inference profile, Bedrock's transparent routing engine analyzes the European boundary. It sees available compute capacity US3 and attempts to route the payload there.
But the enterprise security team's service control policy is an absolute hard wall at the organization level. It says, we only allow actions in U-North-1 and U-West-1. The SCP doesn't care that the Bedrock control plane is trying to gracefully load balance. It just sees an unauthorized region string in the request context, and the IAM evaluation engine drops the guillotine.
Precisely how the evaluation logic works. SCPs override any local IAM permissions.
Yeah.
Even if the developer has full administrator access inside their specific AWS account, the organization-level SCP will deny the cross-region action.
So we have a stalemate. The developer needs CRI to prevent throttling. The security team refuses to open up the SCP to the entire world or even to all of Europe because they want strict control. How does the cloud architect resolve this without violating data residency?
The architectural solution requires understanding how CRI identifies itself to the IAM engine. You do not modify the SCP to blindly allow all actions in US3.
Great, the security team would never allow that anyway.
They'd laugh you out of the room. Instead, you update the SCP to explicitly enable the cross-region inference profile ID.
The profile ID, not the regional ARN.
Exactly. When you use CRI, you aren't invoking a regional model ARN, you are invoking a system-defined profile. The architect must extend the existing SCP's condition block. They add logic to allow the bedrock. Invoke model actions specifically when the target resource matches the eu.amazon.nova-prov 1.0 inference profile, or by using a wildcard like the EU system-defined profile.
Oh, I see. So by explicitly allowing the EU-scoped inference profile in the security policy, you are essentially telling the AWS organization, it is safe to let Bedrock handle the internal routing to any region that supports this specific profile.
Exactly. You cryptographically guarantee that the data will never leave the European boundary because the U profile physically cannot route to North America.
That is brilliant.
It is. You preserve the precise governance required by the legal team, you maintain data residency, and you completely eliminate the regional throttling bottleneck for the development team. And most importantly, that geographic boundary definition is entirely native to the AWS infrastructure layer.
Right. It's not some hacky script.
Right. It is evaluated at the hypervisor network level, rather than being glued together with custom Python scripts in a Lambda function that a junior developer might accidentally overwrite on a Friday afternoon.
Okay, so our backend is now a fortress. We have raw capacity secured with provisioned ARNs. We have traffic routing seamlessly across the globe using CRI, perfectly constrained by SCPs. The backend API is responding in milliseconds, but the lead architect still gets a P1 page on Slack.
Of course they do.
The users are saying the application is completely dead. Why? Because a lightning-fast backend means absolutely nothing if your front-end architecture drops the HTTP connection while waiting for the payload. Let's look at the client side.
This is where we must shift our focus from back-end network throughput to client-side perceived latency and protocol limits.
Our sources outline a very common GenAI architectural pattern here. An internal enterprise AI assistant built as a React single-page application. The front end connects to an AWS Amplify backend, which uses an AppSync GraphQL API to query a Bedrock knowledge base.
Super common setup.
Right. But the users are reporting that the app feels broken. They type a complex question about a legal contract, hit enter, the loading spinner starts, and then nothing. A generic 504 gateway timeout appears. The anti-pattern here is hidden in how the GraphQL resolver connects to Bedrock, isn't it?
Yes. The fundamental anti-pattern is attempting to treat a generative AI model like a traditional REST database query. In a traditional app, you query a database, it returns a JSON object in 50 milliseconds, and you render the screen. But foundation models don't work like that. They generate tokens sequentially.
They write it out.
Exactly. If you configure your AppSync GraphQL API to use an AWS Lambda resolver with a synchronous request response invocation type, you are forcing a massive synchronous chain. The user's browser, the API gateway, the GraphQL layer, and the Lambda function itself must all hang open, synchronously waiting, while the foundation model generates the very last token of its response.
And if we are talking about a complex enterprise query pulling dense data from a vector database and asking an LLM to generate a massive, detailed, cited legal answer, that token generation process could easily take 15 to 45 seconds of pure compute time.
Right. And mechanically speaking, network protocols have strict, non-negotiable timeout limits. Amazon API Gateway, for instance, has a hard integration timeout of 29 seconds.
Which you can't change.
It cannot be extended. If your foundation model takes 35 seconds to generate the full legal response, but the API gateway violently severs the connection at second 29, the user gets a 504 error. And worse, the compute cycles you just spent generating the first 29 seconds of that answer and the money you paid for those tokens are completely wasted. The data simply vanishes into the ether.
So instead of forcing the client to wait in the dark for a 45-second monolithic block of text, we need to bridge the gap between actual latency and perceived latency. We need to stream the text to the user as it's being generated, character by character, token by token.
Streaming tokens keeps the HTTP connection active, constantly transmitting small bytes of data, which prevents the API gateway from triggering its idle timeout. More importantly, it provides the user with immediate visual proof, the time to first token, or TTFT, that the system is actively working, drastically reducing user abandonment.
But wait, implementing real-time streaming through a traditional GraphQL API sounds incredibly painful. If I'm the front-end lead, am I supposed to rip out my entire AppSync architecture, stand up a custom WebSocket server on EC2, manage all the connection states, handle the ping-pong heartbeats, and rebuild the React front-end from scratch? Because that sounds like a 4-month engineering nightmare.
Yeah, rebuilding a custom WebSocket infrastructure from scratch introduces a massive operational burden. You have to handle connection drops, stale sockets, complex state management. The elegant solution the sources point to is adopting the AWS Amplify AI Kit.
The Amplify AI Kit. Okay.
The AI Kit allows you to stream generative responses directly from your existing AppSync GraphQL API using AWS native abstractions. It provides pre-built React components for the front end, and the necessary backend CDK constructs to handle the streaming natively.
So it basically abstracts the entire WebSocket lifecycle away from the developer.
It manages the complex real-time subscriptions under the hood. But a senior architect has to look deeper into the resiliency of that stream. What happens in the real world? The user's on a mobile device, they ask the AI a question, they start receiving a beautiful streamed response, and then their train goes into a tunnel. The 5G connection drops.
I know exactly what happens in a naive implementation. If the connection drops at second 30 of a 45-second generation, the browser throws an error. The user gets out of the tunnel, reconnects, hits refresh, and the system has to start the entire generation process from scratch. They get charged twice for the input tokens, and the user has to wait another 45 seconds. It's a terrible user experience.
And during peak usage, if you have thousands of users dropping connections on mobile networks and triggering those retry storms, you will completely overwhelm your bedrock capacity.
Oh, that's true?
A robust streaming architecture requires an adaptive retry strategy. The Amplify AI Kit, when implemented correctly, monitors for chunk delivery timeouts. You configure it to buffer the already received token chunks on the client side.
Okay, so it remembers what it got.
Exactly. If the WebSocket connection drops, the system doesn't panic. When the network reestablishes, the front end intelligently resumes the stream from the last successfully received chunk, rather than forcing the back end to restart the entire LLM generation.
That is the level of resilience required for production. And to enable this on the back end, the architect has to ensure the Lambda resolver isn't using the standard API. You can't just call invoke model. You have to specifically call the invoke model with response stream API.
Yes. The payload you receive from invoke model with response stream isn't a single JSON object. It's an event stream containing base 64 encoded byte chunks. Your Lambda function has to iterate over that stream as Bedrock pushes the tokens, decode the bytes, and push those individual tokens down the GraphQL subscription to the client.
Wow.
It scales automatically, it keeps the client completely decoupled from direct Bedrock API access, and it provides that near-instant character-by-character feedback loop.
Okay, so we've got the capacity provisioned, we've got global routing figured out, and we've got a beautiful, resilient streaming UI that survives network drops. But let's take a breath.
Fair enough.
Streaming text instantly to a user screen is fantastic. It looks great in a demo. But if the AI is confidently streaming absolute hallucinations at the lightning speed, we have a much bigger problem. A fast, highly available wrong answer is still a wrong answer.
And in enterprise environments like healthcare, legal, or finance, a fast wrong answer isn't just an annoyance, it is a critical liability.
Which brings us to retrieval augmented generation, or AG, and the science of chunking. We need to fix how we feed the model its data. Let's establish the baseline here. The foundational concept of AG is that foundation models, no matter how massive, do not inherently know your proprietary company data.
No, they don't.
They don't know your HR policies, they don't know your private source code, and they don't know your specific medical trial results. You have to retrieve the relevant documents from a database and pass them into the prompt as context. But you cannot pass a 5,000-page technical manual into a prompt.
Well, you could, but your context window will overflow and the cost will be astronomical.
Right, so you have to chop the manual up into smaller pieces or chunks, turn them into vector embeddings, and only retrieve the specific chunks that are mathematically relevant to the user's question.
That is the standard AgHab pipeline. And the most common anti-pattern here is what the industry calls fixed-size chunking.
Ah, the meat cleaver.
Exactly. A team will write a simple Python script that blindly slices their massive text corpus into rigid blocks of, say, 500 tokens or 1,000 characters. It just runs a split function, completely ignoring the semantic meaning of the text.
Fixed-size chunking is like taking a highly technical textbook and chopping it up with a meat cleaver at exactly every third page, regardless of whether the blade falls at the end of a chapter, the middle of a paragraph, or right between the subject and verb of a critical sentence. It's brutal.
It is a mechanical operation clumsily applied to a semantic medium, and it destroys context. Imagine a complex legal contract or a scientific methodology. If a critical argument or the relationship between a complex financial metric and its explanatory footnote is physically severed by that meat cleaver and split across two different 500-token chunks.
The model loses the relationship entirely.
Yes. When the user asks a question about the metric, the vector database might retrieve the chunk containing the number, but completely miss the adjacent chunk containing the crucial explanation. The AI then hallucinates the explanation because it lacks the context.
So the legacy approach to fixing this was awful, right? Teams would try to build custom SageMaker query decomposers, host custom sentence transformer models on EC2, or build massive machine learning re-ranking pipelines. The operational overhead was staggering just to chop up text correctly, but the modern AWS native approach is using Bedrock's built-in advanced ARG capabilities. Specifically, I want to dive into semantic chunking and hierarchical chunking. Let's unpack semantic chunking first. How does it actually differ from the meat cleaver approach under the hood?
Semantic chunking abandons the rigid character count. Instead, it splits documents based on meaning. It analyzes the text and actively looks for shifts in topic or intent. In Amazon Bedrock knowledge bases, you can configure this natively. It uses a breakpoint percentile threshold. Let's say you set it to 95% and a buffer size, like 3 sentences.
Okay, so it's looking for a 95% change in topic.
Sort of. Under the hood, the system is calculating the vector dot product of adjacent sentences to determine their semantic similarity. When the mathematical difference between two adjacent sentences exceeds that 95% threshold, the system recognizes the topic shift and creates a chunk boundary right there.
Oh, that makes sense. And the buffer?
The buffer ensures that a few sentences overlap across the boundary, maintaining a smooth semantic transition. This guarantees that a single cohesive thought, like a specific firewall configuration rule or an HR PTO policy, remains entirely intact within one chunk, rather than being arbitrarily severed.
That makes perfect sense for standard enterprise documents like policy manuals or IT runbooks. But what if the data is astronomically larger and more complex? Our blueprints detail a scenario with a massive pharmaceutical company.
I remember this one.
They have an Amazon Bedrock knowledge base connected to a multi-node Amazon OpenSearch service cluster. They are querying 25 million dense scientific papers. The researchers are complaining that the AI is producing inconsistent answers. It cites completely irrelevant sections when a complex query spans the methodology, the results, and the discussion sections of a single paper.
Yeah, when you scale up to 25 million highly structured, multi-page scientific documents, even semantic chunking breaks down. Why? Because complex scientific concepts are distributed across multiple sections. The answer to a researcher's query might depend on the specific laboratory methodology described on page 2, combined with the statistical result detailed on page 8.
Right, they're not next to each other.
If you use standard chunking, the vector database retrieves highly specific, isolated snippets of text, but strips away their surrounding rationale. The LLM gets a fragment of the result without knowing how the experiment was conducted. This is where hierarchical chunking becomes the optimal architecture.
Hierarchical chunking. Walk me through the architecture of that. How does it link data?
Hierarchical chunking creates a multi-resolution structure inside your OpenSearch database. Instead of just creating one size of chunk, it creates very small child chunks, let's say 200 tokens each. These small chunks are highly precise. They are mathematically perfect for exact vector similarity matching against a specific narrow user query.
Okay, so they're easy to find.
Very easy. But crucially, during the ingestion phase, every single 200 token child chunk is programmatically linked via an ID pointer to a much larger parent chunk, perhaps a 1,000 or 1,500 tokens in size.
I love this concept. So the small 200 token child chunk is like finding the exact index term in the back of a massive reference book. It gets you exactly where you need to be. But instead of just handing the AI that one single sentence to base its answer on, the system follows the pointer, retrieves the 1,500 token parent chunk, and hands the AI the entire chapter to read.
That is the exact mechanic. When the vector database calculates that a specific child chunk is a highly relevant match to the user's prompt, the system intercepts the retrieval. It doesn't pass the isolated child to the foundation model. It retrieves the linked parent chunk and passes that broader narrative context into the LLM's prompt window.
Which fixes the hallucination problem.
Exactly. This preserves the section-level continuity of the scientific paper. The foundation model receives the precise methodological detail it needs to answer the question and the broader discussion framing, which actively prevents misinterpretation and hallucination.
Now let me throw a curveball at you. Let's say I'm building a medical RG system. Medical terminology is notoriously brutal for search engines. You have massive hyphenated words, overlapping acronyms, specific alphanumeric drug codes. If my RG system is failing to find exact medical matches, my first instinct as an engineer is to just throw more compute at the embedding model.
Of course it is.
What if I just take my standard embedding model and crank up the vector dimensions? If I increase the vector embedding dimensions from 384 to 1536, won't that higher resolution mathematical space capture more detail and get me better exact matches?
This is one of the most pervasive misconceptions in generative AI architecture. Increasing vector dimensions adds massive computational cost, inflates your OpenSearch storage overhead, and increases network latency. But it fundamentally fails to solve the problem of exact terminology matching.
Really? Why?
You have to understand how pure vector similarity search operates. It maps semantic meaning into a multidimensional space. It is incredibly good at understanding the vibe of a text. It knows that the phrase heart attack and the term myocardial infarction are semantically close together in that space.
Yeah.
But dense vectors frequently underweight exact character matches for highly specific alphanumeric acronyms, drug names, or product codes. If a doctor searches for a highly specific protein string like BRCA1 mutation, the vector search might retrieve a document about a completely different genetic mutation, simply because the surrounding context about oncology and screening is semantically similar. It retrieves a document that feels right, but misses the exact alphanumeric acronym the doctor actually queried.
Which in medicine is close, but no cigar. And in healthcare, close is completely unacceptable. So if cranking up the vector dimensions is a costly dead end, what is the correct architectural move for exact matching?
The correct architectural move is implementing hybrid search. You must combine the semantic power of dense vector similarity search with the absolute precision of traditional lexical keyword matching, specifically the BM25 algorithm.
Okay, BM25, for those who haven't tuned search engines recently, what's that doing?
BM25 isn't looking at the semantic vibe of the word. It is a statistical function calculating term frequency and inverse document frequency. It is literally counting exact keyword matches and weighting them based on how rare the term is in the overall corpus.
So if a document contains the exact string BRCA1, BM25 flags it immediately, regardless of the surrounding context.
Precisely. Amazon OpenSearch Service supports hybrid search natively, and Bedrock knowledge bases integrate with it seamlessly. Keyword search ensures absolute lexical precision for exact acronyms and IDs, while vector search captures the broader semantic context and synonyms.
Then it just combines them.
Right. By normalizing and blending the scores of both approaches at retrieval time, you dramatically improve both recall and precision, completely avoiding the massive compute overhead of unnecessarily large vector dimensions.
Okay, that is a golden nugget of insight. Don't fight the math of dense vectors when a traditional statistical keyword index does the exact matching job perfectly. Combine them. Let the tools do what they are best at. So let's take stock of the architecture we've built so far.
We've covered a lot.
We really have. We have raw compute capacity provisioned and protected from cold starts. We have global scale routing seamlessly with cross-region inference, safely boxed in by organization SCPs. We have a beautiful, resilient front-end streaming tokens through WebSockets. And we've grounded the AI's brain with highly precise, hierarchically chunked, hybrid search knowledge. The AI is smart, fast, stable, and accurate.
But we aren't done.
No, we aren't. Because if you are operating in a true enterprise environment, healthcare, heavy industry, finance, aviation, you cannot just unleash an autonomous AI on your back-end systems and hope for the best. Let's move into our final area, bulletproof governance and orchestration.
Governance is the ultimate differentiator between a flashy hackathon toy project and an enterprise-grade system. When an AI interacts with the physical world, making automated financial trades, suggesting medical treatments, or initiating hardware maintenance actions, you need rigid guardrails, unalterable audit trails, and frequently mandatory human oversight.
Let's ground this in a real-world physical scenario from the blueprints. We have an elevator service company. They've built an AI assistant that ingests real-time telemetry data from elevators across a massive city. Thousands of data points per second are flowing through Amazon Kinesis data streams.
Lots of data.
Right. The AI analyzes the vibration anomalies and the motor temperatures, and it autonomously generates detailed maintenance recommendations and dispatches for the field technicians. But here's the regulatory catch. New safety rules dictate that a certified human technician must review and explicitly approve every single AI-generated dispatch recommendation before any work order is actually created in the backend database. And every single human decision must be cryptographically audited.
If you attempt to build this human-in-the-loop workflow using traditional messy chains of custom AWS Lambda functions, DynamoDB state flags, and SQS dead letter queues, you're going to create a fragile, unauditable mess.
It's just spaghetti code at that point.
Total spaghetti. You will spend half your engineering cycles writing custom state management logic, building polling loops to check if the human has clicked approve, and writing dead letter queue handlers when the polling times out. The AWS native, architecturally sound solution for this is AWS Step Functions.
Step Functions acts as the central orchestrator. It manages the entire state machine of the workflow.
Yes, Step Functions orchestrates the microservices. And for this specific regulatory requirement of human intervention, Step Functions provides a brilliant integration pattern called Wait for Task Token.
Okay, let's get into the weeds on this. How does Wait for Task Token actually suspend compute without racking up a massive AWS bill? Let's trace the execution. The workflow processes the Kinesis data, the Bedrock AI generates the maintenance recommendation, and the workflow transitions to the human approval state. When Step Functions enters a Wait for Task Token state, it generates a unique cryptographic string, the task token. It sends the AI's recommendation payload, along with that token, to a system the technician monitors. It can publish to an SNS topic that triggers an email, or push the data to a custom web dashboard.
Right.
Crucially, the moment Step Functions sends that token out, it deterministically pauses the workflow execution. It just stops. It unloads the state from active memory. It does not consume active compute pulling a database. It does not run a while loop. It waits in a suspended, dormant state for up to a year if necessary, costing you practically nothing in active compute.
It just chills out until the human is ready to look at it.
Exactly. When the elevator technician finishes their coffee, logs into the dashboard, reviews the recommendation, and clicks the Approve button, the front-end React application makes a direct API call to Step Functions called sendTaskSuccess. It passes that exact cryptographic task token back in the payload.
Okay, and then?
Step Functions matches the token, immediately wakes the suspended execution up, and continues to the next step, creating the work order. If the technician clicks Reject, the front end calls sendTaskFailure, and the Step Function state machine elegantly routes to a different error handling branch.
And from a compliance perspective, this provides an immutable stateful audit trail. Step Functions natively records exactly when the workflow entered the paused state, exactly what payload was sent to the technician, exactly when the sendTaskSuccess API was called, and by which IMM user. All of these state transitions are logged in AWS CloudTrail, automatically satisfying the strictest regulatory safety audits without writing a single line of custom auditing code.
It completely removes the polling loops and database state flags you'd normally have to build and maintain.
That is incredibly elegant. But let me challenge you on the physical scale of step functions. Let's push the architecture further. Let's say we are building a complex multi-agent system. We are implementing a React pattern reasoning and acting.
Okay.
We have multiple AI agents interacting. We have a description generator agent, a technical specifications validator agent, and a brand voice consistency agent. They are all passing their internal reasoning traces, their scratchpad notes, and massive generated documents back and forth to each other as JSON payloads. If I try to push all that data through a step function state machine, won't I hit a wall? I know step functions has a strict maximum payload size limit.
It does, 256 kilobytes.
Right. If I have a 5 megabyte reasoning trace and step functions caps at 256 kilobytes, my first instinct is to try and compress the JSON, or maybe write a script to chunk the payload and send it through multiple state transitions in sequence. Does that work?
You could attempt to gzip the JSON payload, but you will still inevitably hit that 256 kilobyte ceiling as your multi-agent reasoning traces grow. And chunking the payload across states completely breaks the atomic nature of the workflow. Passing massive AI reasoning traces and generated documents directly between workflow states is a very common failure mode for developers new to orchestrating Gen AI. Your workflow will hit that quota and fail catastrophically.
I've actually hit that limit before. It's miserable. So how do senior cloud engineers bypass this?
The architectural pattern involves externalizing the state. You utilize Amazon S3 as the actual data bus, and step functions really acts as the control plane.
So how does that state machine definition actually look in the JSON configuration?
Let's say state A is the generator agent. State A does not return the 5 megabyte generated document to step functions. Instead, state A writes the document to an S3 bucket. Then it returns a tiny JSON object containing only the S3 URI, the exact pointer to the file, like s3.mybucketexecution123draft.txt.
Oh.
Now, inside your step functions definition, you use the result selector field. Result selector parses the Lambda response, extracts just that S3 URI string, and uses the result path field to inject that tiny pointer into the main state payload.
Ah, I see.
State B, the validator agent, receives a microscopic 200-byte JSON payload containing the URI. State B's Lambda function reaches out to S3, downloads the massive file, processes it, writes its own validation output back to S3, and passes the new URI to State C.
That is classic pointers in computer science, just applied at a macro cloud architecture level. You pass the reference, not the value. It keeps the step function state payload perfectly lean, sitting at maybe 1 or 2 kilobytes, well under the 256 kB quota, while the actual heavy lifting happens over in S3, where storage capacity is practically infinite.
And it preserves perfect observability, because if an execution fails, your step function's execution history contains the exact S3 object keys for every single step of the multi-agent reasoning process. You can download the exact files and see exactly what the AI was thinking at state B before it crashed at state C.
And we can use step functions to fundamentally alter the latency of massive workloads by parallelizing them, right? Our sources mention a financial document analysis system. They're processing massive batches of quarterly financial reports. For every report, they need to run 3 distinct foundational models. One for financial entity extraction, one for market sentiment analysis, and one for regulatory compliance checking.
A very heavy workload.
Yeah. Currently, the legacy architecture runs this sequentially in a single Lambda function. It calls model 1, waits, calls model 2, waits, calls model 3, waits. It takes 45 seconds to process a single batch. The new business requirement is to get that under 10 seconds.
This is where step functions parallel state completely transforms the latency profile of Gen AI workloads. If those 3 analyses, extraction, sentiment, and compliance, do not logically depend on each other's outputs, there is zero architectural reason to run them sequentially.
They can all happen at once.
Right. The parallel state allows you to define 3 distinct branches in your state machine. When the workflow hits that state, step function simultaneously invokes 3 separate Lambda functions, which concurrently call Amazon Bedrock.
So instead of the total time being model A plus model B plus model C,
The total batch processing time drops to the latency of the single slowest model invocation. If the compliance check takes 9 seconds and the others take 4 seconds, your total execution time is 9 seconds. You drop a 45-second monolithic bottleneck down to under 10 seconds.
that's a massive improvement.
Huge. You vastly improve the throughput of your system without writing complex, bug-prone asynchronous coordination code in Python or Node.js. The state machine handles the fan-out and the fan-in natively.
Okay, one final scenario on governance. Let's talk about dynamic configuration, specifically prompt gating. What happens when things go wrong in production? Let's say an AI agent in production starts hallucinating wildly. Or worse, a developer accidentally hard-coded a stale, expired database secret into a prompt template, and the AI is actively throwing database connection errors to the user. I need to stop it instantly. I cannot wait for a 45-minute Jenkins CI/CD pipeline to build, test, and deploy a code fix across all my regions. I need to change the AI's brain in milliseconds.
For immediate dynamic configuration changes at runtime, hard-coding prompts into your application code is an anti-pattern. AWS App Config is the architectural tool of choice here. You externalize your prompt templates, your model routing rules, and your agent hyperparameters into app config profiles.
So the prompt lives in the infrastructure, not the Git repository.
Exactly. During runtime, your Lambda functions pull app config and cache the prompt template. If an agent goes rogue in production, the lead architect can log directly into the app config console or use the CLI and instantly roll back the configuration to a previous stable prompt template.
No code deployment required.
Absolutely no code deployment. And because app config integrates natively with step functions, map states, and Lambda extensions, the parallel agents fetch the updated safe configuration from the local cache on their very next invocation. The bleeding stops instantly.
That's incredible.
You can even use app config for advanced feature flags. You can configure it to gradually route 10% of your production traffic to a new prompt template or a new Bedrock model version, monitor the CloudWatch error rates, and automatically roll back if the new model starts hallucinating, allowing you to test GenAI behavior safely before a full 100% rollout. It gives you real-time, granular control over the cognitive behavior of your distributed system.
This has been an absolutely phenomenal breakdown. We have covered an immense amount of ground today, pulling apart the blueprints of enterprise-grade AI. Let me try to synthesize the architecture we've built. We've essentially constructed a complete, highly resilient nervous system for a generative AI application.
We really have.
We started with the muscle, securing raw compute capacity. We learned that a single model IT string is the difference between actually utilizing your expensive provision throughput and getting violently throttled in the multi-tenant on-demand queue. We built the reflexes, using cross-region inference to gracefully handle follow-the-sun traffic spikes while navigating the complex IAM logic of service control policies to ensure European data legally stays in Europe using specific inference profiles.
The routing layer is so crucial.
It is. From there, we secured the communication layer. We abandoned synchronous Lambda HTTP resolvers that cause fatal API gateway timeouts. We embraced the Amplify AI kit to stream tokens natively through GraphQL WebSockets, maintaining resilient client connections that buffer chunks and adaptively recover if a user drops offline in a tunnel.
Keeping the user engaged.
Right. Then, we grounded the AI's memory with advanced RAG. We threw away the blunt meat cleaver of fixed-size chunking. We embraced semantic chunking for policy documents, relying on vector.products to find topic boundaries. We built hierarchical chunking for massive scientific corpora, giving the OpenSearch database the precise 200-token child chunk for exact matching, and giving the LLM the massive 1,500-token parent chunk for narrative context. And we proved that mindlessly increasing vector dimensions isn't a silver bullet. Hybrid search blighting BM25 term frequency with dense vectors is the absolute key to exact medical and legal terminology.
Exactly. Let the search engines do what they're good at.
Finally, we locked down the entire brain with step functions governance. We implemented mandatory human-in-the-loop approvals with the .wait for task token API to keep the regulators happy without paying for idle compute. We bypassed the 256 KOB state payload limit by passing lightweight S3 URIs, acting as cloud scale pointers. And we accelerated batch processing from 45 seconds down to 9 seconds using parallel states, with app config standing by for instant zero deployment pumped rollbacks.
It is a comprehensive, production-ready blueprint. It shifts the focus from experimenting with AI to operationalizing it securely.
So I want to leave you, the architect listening to this right now, a final provocative thought. As cloud architecture evolves at this breakneck pace, the hardest part of artificial intelligence is no longer the artificial intelligence itself, the foundation models. They are commoditized compute engines. You can switch between an Anthropic Claude 3 model and an Amazon Nova Pro model with a single API string change. The models will only get faster and cheaper. The true, lasting competitive advantage for a senior cloud architect now lies entirely in the connective tissue. It's the routing intelligence, it's the semantic chunking boundaries, it's the state management, the throttling resilience, and the rigid governance workflows. If the foundation model is just a black box compute engine, how much of your current infrastructure is needlessly trying to peek inside the box, rather than mastering the plumbing that surrounds it?
That is the exact question every engineering team needs to answer before they push to production.
Remember the disaster scenario where we started? You don't want to be the architect whose brilliant prototype collapses under the weight of production load because you built it on fragile legacy ML foundations. You want to be the architect who designed the plumbing so elegantly, so resiliently, that when 10,000 users hit the system at the exact same second, the architecture doesn't even blink. Keep diving deep. Thank you for joining the conversation.